Hello, everyone. Welcome to this webinar. It's 5:30 p.m., so we are starting with this webinar. I also tell you now that the recording will be shared in our YouTube channel. So in case you are not able to follow all the webinar, you will be able to see it in another time. And also, in case you know someone who is not able to attend this webinar, tell them that they will find everything in our YouTube channel. And we will also try to share the video in our LinkedIn profile and so on. So, as I said, welcome everyone to this webinar. Before starting, a very short premise to also explain to you why this webinar. As you can see, we want to introduce the new version, the one that we have issued just 2 weeks ago. And let's say that this webinar is also something that we want to be the first of a long series. Let's say that from now on, we would like to improve our communication in this way. At each new version, we will organize a webinar in which we wanted to introduce and to present the new features of the software. Let's go on anyway with the webinar itself. So as you can see, we are two presenters. Me, Daniele Cuccarollo from Sint, and also my colleague Mauro Passarotto. We also have two speeches, one each, and consider that we would like to handle all the questions at the end of both speeches. So not at the end of the first, but at the end of the second speech, there will be the time that we wanted to use for the questions. This is due to the fact that we do not want to exceed with the time needed. So let's go on with the presentation very quickly. The main new features are the following ones. So the most important as dimension also is the electromagnetic forces. And in fact, we have introduced the management of the conductor continuity to infinite as a conductor property. We have introduced also very important the spark gap SPDs for XGSLab. We have also improved the way to handle the software by introducing dedicated tools for the manual input of injected currents, external electromotive forces, longitudinal and transverse impedances, continuity to infinite of conductors, and reference points. We have also answered to a request that was the introduction of the on-tag parameter in the scheduler. And we have also the new harmonic impedance graphical output in XGSATD. Also, this tool was meant to make easier the job of some of our users that deal with the TD module. So we are going to start with the first speech about the first contribution about the electromagnetic forces. Just let me 1 minute.
Hello and welcome to this first presentation of our today webinar, which will be about electromagnetic forces and effects calculation. We will just have a quick glance at electromagnetic forces first and then to the effects with a practical demonstration. So I want just to recall that electromagnetic forces are composed of two terms. The first term, which is the less important for our purpose today, is the Coulomb force, which is due to the electric field. The other one, which is more important, is the Laplace force, also called and known as magnetic force. This during faults in substations or power plants in general are focusing on this condition. Specifically, we can recall these 3 plus 1, let's say, standard, which are international and coincident European standard, and the US standard. And by the way, it's important to recall and remember that the IEEE 605 standard mainly refers to the international standard when considering the effects of the forces calculation. So the magnetic force, according to the standard, is computed by assuming a three-phase or line-to-line fault. It considers three or two parallel conductors only that are laying on the same plane. Finally, it considers also an indefinitely long conductor, which can be traduced in the situation in which the conductors has a distance which is much smaller than their length. Given these assumptions, you can write this equation, which has mainly some geometrical terms, the length and the distance between conductors, and one factor which is dependence on the peak value of the short circuit current, and another factor which depends on the short circuit type. Specifically, this factor has a value when in case of a three-phase fault and is referred to the central conductor only. Uh, in case of a line-to-line fault, the value is different and is symmetric for the two conductors faulted. Why do we consider the peak value? Because the actual curve of the magnetic force during a fault is far from being sinusoidal, as explained in Sigre 105. We can see in this paper that there are mainly four terms. Two of them are sinusoidal, the other two are not, and two of them, let's say two crossed, two of them are steady and the other are decaying. This situation is due to the fact that when a fault is happening, the current, the short circuit current, has a non-sinusoidal shape, especially during the initial instance. And for this reason, what can be done from a practical perspective is to use a peak value, and this approach will be the one also put in place in the software, so during the computation and especially during the computation of the effects. More than this, it's important to notice that nothing is proposed in the standard and in the SIGRE in regards of realistic conductors placing in the 3D space. in the 3D space. And this traduces in the fact that rigid conductors are considered parallel coplanar and indefinitely long during all the dissertation contained in the standard and, for instance, in the SIGRE. And this is why our software is trying to provide an answer in this respect. So let's see how we can do this in practice by using the software. Okay, so let's start from scratch. We can, in this case, open a project. This is the one you can find in the setup, the tutorial. And in this example, we can see that everything in the XGSAFD model has been tweaked, and specifically the waveform and the soil model in this case is a uniform model because it's the best choice for the purpose we have to compute EM forces and effects. And then we can see the data and import the data. Of course, you will need the XF if you want to import it. Everything has been organized in such a way that layers are separated. So each phase and each part of the substation in this case has a distinct layer, and once everything is coherent, we can import the layers and then obtain our conductor list. Once we have imported the conductors, we can notice that each tag and layer are describing a subset of our substation. Here we can see that each bar has a separate layer depending on the phase. And given this, we can then proceed, and in this case, by filtering some part of the conductors, we can set, for instance, in this case, the source of the current and the voltage. Is quite important to set both of them if you want to compute the forces, because otherwise the software will give you an error. In this phase, it is of paramount importance to double check the sources, the values you are inserting, in order to then obtain a coherent solution. Once we have done this, we can debug the conductor, and in this case, notice the fragmentation and the subdivision of the conductors. This subdivision will reflect in the subsequent part of this example. In this case, high fragmentation has been used, and this is very important when performing such a computation because it allows you to obtain a more accurate description of the force variation along the conductors. If we now go back again to the conductor list, we may notice that we have different types, in this case, of conductors set up. We have both overhead lines and pipe type. For instance, the pipe type, you can find it in the standard conductors library. In this case, be selected as a favorite, and you can see here all the details. So it's a tubular type of rigid conductor that has been set for the most of the conductors. Once everything is okay, we can then proceed and launch the computation. The computation is very quick, given that we are using SURSI, which for this type of calculation, I mean, the electromagnetic forces is the most suitable one. We can actually compute the distribution. Before do that, the distribution of the force. Before do that, it's quite smart, in my opinion, to recheck, especially if you were dealing with first simulations of this type, check the actual subdivision of the conductors in terms of currents and potential in order to observe and detect whether there might be some differences with respect to your desire, let's say. And once you are fine with this, you can actually calculate the forces. You can also select a um, sampling number by using the box there. And of course, there is like a default value which is set to 1000 subdivision. Once we have selected it, we can launch the calculation, and also in this case, you obtain a very quick one. At this point, you can actually focus on the results and display them. You have different options as plot types. You have the 2D, the 3D one, and given the 3D, you can see the variation of the force in the space, and you can also filter some single conductors. You can also select one single conductor and plot it as a 1D plot, so you can see the variation of the force along the conductor. In this case, we just selected one conductor. And given the data you are seeing on the screen, you can also export them as a comma separated value in which you can appreciate all the small variation and all the components of the of the obtained force. You can do that also for the 3D representation. In this case, you'll obtain a set of three coordinates that will give you the actual positioning of the force with respect to the element of the fragmentation in the 3D space. Let's now have a break on some slides again before moving to the effects calculation on the tool. Mainly the standard reflects the fact that from the computation of the electromagnetic force, one can compute the effects in two conditions when considering rigid conductors or when considering flexible conductor. In the tool, for the moment, only the case of rigid conductor has been considered and implemented. If you consider the forces, you can do whatever you want, also in terms of used conductor. For instance, you can use as a conductor type an overhead line, you can use victim sources, whatever you want. On the other side, when moving to the effects, and especially when, as we will see, when importing some forces, you have always to keep in mind that the effects are valid only if the conductors are rigid. The philosophy or the approach used in the tool has the requirement of fulfilling the fact that during a fault, the mechanical effect computations regard both static and dynamic phenomena. This is explained again in the SIGRE 105. Basically, especially for the dynamic effects, it's quite impacting the way in which the mechanical frequency or natural frequency and the sinusoidal frequency of the electromagnetic force are interacting as shown in this plot. Thus, since static loads and stresses might be computed independently from the standard, but an accurate dynamic analysis would have been possible just by resorting to an accurate and customized finite element analysis. In the tool, you will find the electromagnetic calculation for the forces, which is general and can cover any possible case and configuration. On the other hand, the effects calculation will use the standard as a guide, especially for the dynamic analysis. And now let's see this in the tool. So let's go to this second part, and we will start again by opening the project, so from a blank paper, let's say. And in this case, we will try to use the tool, the EMFX tool. Before doing that, you have to set a standard, otherwise you will not able to access to it. This is the interface you will find, and the very first box, it's the description box in which you can set a description which will be used also to recall and re-upload the calculation you have been performing in this project. So whenever you are calculating and saving the project, the new description will be added to the list of available description. In this case, we are now adding another description. You have the frequency that is automatically detected from the waveform in case there is one. And here you have the import results option, which is blocked because you don't have any available results in terms of electromagnetic forces, at least for the moment, of course. So in this case, we will use the tool in its standalone mode, given that we don't have any electromagnetic force calculation available. So to use the tool in such a way, you have to fill the boxes and cells which contains the required parameters and data, which, by the way, reflects almost exactly what is required and what you can find in the international standard. In this case, we will use as electromagnetic force input the locally calculated one because we just have that one. In the following part, we have the correction factors and later the mechanical data. We will now focus on the correction factors, which is quite important because we'll take into account of the non-perfectly sinusoidal effects and behavior of the force in such a way we have seen in the very first part of this presentation. We now have the mechanical data, which is linked to a new library, which is this one. In this new library, you can offline, let's say, so before opening the tool in a separate moment, prepare all your indeed mechanical data or busbar types, which are described from the mechanical point of view. So it's quite similar, but not equal to the conductors list. For instance, here you have the same label, but the reported information is quite different. It's important to always keep on your mind that there is no automatic link between the conductors library and the mechanical data library. So even if the two descriptions are the same, the tool is not linking the properties of the conductors. This is well explained in the user guide if you are interested more into this respect. So once we are obtain our mechanical data enter, we can move on and select the span type, the supports distance, all items that you can easily find in the international standard. You can also decide whether to apply and download, and then by clicking the calculation, you obtain all your results, which are also displayed in the plot put on the side of the main interface. In this case, you can see that the bus bar was able to sustain the short circuit, so the outcome of the result of the computation is positive. And as a final part, you can also export your calculation as an Excel spreadsheet, and you will find there all the selected and set values for your calculation. And we are now going to see how to use the tool in its import mode. So we start noticing that again the import results side is disabled, but by performing an electromagnetic force calculation, and reopening the tool again, it will be active. So the point is using the more or less same interface of the distribution plot of the force to actually import a value of a conductor or from a conductor. The conductor is described and detailed thanks to these cells here, in which you can check the conductor ID you have selected, the average current in the conductor, and the composition of the force based on the support direction. This is a quite important item to be entered in the interface, which give you the direction of the supports, in the sense that, for instance, as in this case, if the supports are sticking into the ground, you will have a support direction vector which is 0, 0, 1, as in this case. If, for instance, your support is placed and attached to a wall, it will be different given the 3D orientation of the space. And so you will use, for instance, a 0, 1, 0, and so on. So this upper direction interacts with the way in which the force is subdivided into its normal or orthogonal and parallel direction or component. And so when you are setting this parameter and when you are importing, you have to be very careful in choosing this item. Given this, once you have decided, the the software computes an average along the selected conductor you have double clicked. Once you are okay with your import conductor force, you can also use the local calculation to make a comparison. For instance, by inserting a short circuit current and an average distance which is comparable with the actual one you have in the 3D model you have imported, you can compare the imported value, those two, with the locally calculated one. And you can also see if there are some discrepancies, as in this case. This, in my modest opinion, is one of the most powerful feature and consequences you have when using this tool with the import mode on, let's say. And so I will encourage you to make such a comparison also by resorting to the several and different filters or several views you can have by interacting with the 3D plot or 2D plot option. Just a further comment now about the 3D TXF model you are importing. In fact, given that the software is performing an average along the conductor, you have to be very careful when building your initial model, in the sense that you have to place the conductors as items that are going from one clamp to the other, from one support to the other support. By doing this, when performing the average, you will just select one support to support span, as it should be in the application of the international standard. Given this, you can go back now to your main interface of the tool, and you can now select import force, import results, and then by filling the same areas as in the standalone mode, you can achieve your final result in a quick and straightforward way. Now, just to give you an idea, I'm showing you how you can select from the description a previously calculated item, as you can see. And also you can, of course, as an eventual step, export, as we have seen before, your calculation. In this case, you will have input from import result. And we are over. So I thank you for your attention. You can find much more details in the tutorial you can find in our YouTube channel. And of course, I'm available if you have a question to which I'm happy possibly to answer.
Hello and welcome to this second part of the webinar. In this second part, we will see some of the new features that we have introduced in the 10.3 release of XGSLab software. The features that we are going to see are, first of all, the ones about the input of external entities in the conductors. The example that we are going to see is really very simple, and it is just with two conductors. The longest one is a pipeline, a very common pipeline, and the shortest one is an insulated conductor. The insulated conductor will be used as a victim and will be set up in order to be the source of magnetic induction. So first of all, we are going to see how it is possible now with the new version to inject a current. We can single click on this tool. The cursor of the mouse is updated, as you can see, and there is also a pre-selection that shows you where the current will be injected in case you click. So single click, and this dialog box opens, and in it you can set up a name for the injection point. You have some information about the conductor identifier, the elements identifier, the tag where you are applying the current, and you can set also the value of the current. Consider that it is in polar format because in the settings of the software now the format selected is the polar one. So we can set 1000. We can extract also the current in order to use as the victim as a source of magnetic coupling. And we can set the value that is the same with the phase that is 180 degrees. We can go on with the new tools. Let us concentrate now on the continuity to infinite. As you know, in the past it was possible to select a conductor, right button of the mouse, and we could set up the simulation to infinite of the conductor. This is possible, this is still possible, as you can see, but now we have modified the application, the possibility to apply the continuity to infinite. And also we have modified the way to handle that continuity to infinite. That is to say that we can single click on this. You can see the cursor, and also the pre-selection is adapted to the infinite feature. You can single click without setting any value. You have the continuity to infinite applied. Why this? Basically because from now on we will consider the continuity to infinite as a property of the conductor. So you do not have, or basically it is not important that the user knows what is the value of the transverse impedance, that is the one of the characteristic impedance, and so on. It is important that the user is aware of the fact that this conductor is set up in order to continue to an infinite distance. And the most important detail of this new feature is that if you change the soil model or the diameter of the pipeline in this case, or the material of the pipeline, or the conductor that you are using for the pipeline, the value of the ZT that is used to simulate the continuity to infinite is automatically updated. So this is the most important news about this feature. The continuity to infinite becomes a property of the conductor. You can set it also on this. Consider that even if it is a property of the conductor, if you edit this conductor and maybe you can force the value of the impedance, because anyway the continuity to infinite works still works in the same way it has always worked. If you modify this value that were set with the property continuity to infinite, the software warns you that if you apply this modification, that will be not anymore a property, but it will become a normal ZT. So, as you can see, this has been transformed in a normal ZT that, in case we modify the conductor, will remain with its value that is now set, without any automatic updating that we mentioned before. So we can get back to the infinite. Other features that are available with the new version of the software are, for example, the external impedances. We can set up, for example, a longitudinal impedance here. We have also the name of the site. We can set the value. In this case, we are going to set 10 millions in order to have an insulating joint. And we can also set up transverse impedances, but with some very important news, that is to say, with the possibility to trigger. So we have introduced, as you have read maybe in the notification of the new version, we have introduced the source protective devices, both longitudinal and transverse. So basically, what are they? They are some impedances, in this case transverse, that by default at the first run of the software, they have this value, 10 millions of ohm. You have to, in order to set up them, you have to set up a threshold and a value once it is, in case it is, once it is triggered. So let's suppose it is 2 ohms. So how does this entity works? Basically, at the first run, all the SPDs has got this value of impedance. At the end of the first run, the software checks if any of the SPDs has got a value of drop of voltage along them that is above the threshold. In case you have just one SPD, let's suppose that is above, that has got a drop of voltage above the threshold, you have that SPD is triggered, that is to say that is set as triggered. The calculation is relaunched, and at the second run, the value of the ZT is not anymore this one, but it is the one that is set as triggered. Consider that in case you have many SPDs, at the end of one run, you have many SPDs that are above the threshold of voltage. In that case, you trigger just one of them, and you trigger the one that has got the highest ratio between the drop of voltage along it and the threshold set. And so you have multiple runs, and at each run you trigger one SPD. And this goes on until no SPD has the drop of voltage above the threshold. So all the SPDs could be triggered at the end or not. It depends. So we can set this one. And we can set also this other one. So we can set the threshold and the ZT. We have set some entities, and now we can run a debug and also a calculation. Concentrate on the message window. At the end of the calculation, there is a list of all the SPDs that has triggered. Consider that this list is in the order that they have triggered. So in this case, we have that both the SPDs we had have been triggered, and we have this specified table for the SPDs where we have a column triggered that is also highlighted in case the triggering has occurred. We can also have a look at the potential distribution along the pipeline, and we can see that this is what happens. We can make a slight modification in the model in order to try also to use a longitudinal impedance. In this way, we can just click on that. As you can see, when you click an SPD where it was present an impedance, the value of the impedance is anyway collected, so you modify what is present. We can set also in this case 50, let's suppose, and here a very low value of impedance, and we can apply. We can run also this calculation. Let's have a look at this. So this is very interesting because at the end of this calculation we have that with 3 SPDs, just 2 of them have triggered. So if we have a look at this table, in this case we have 3 SPDs, 2 of them have triggered, and one it is remained as it was at the beginning. In fact, as you can see, the drained current from that ZT is 0 because the value of the impedance is very high. In this case, if we have a look at the potential along the pipeline, we have that now the behavior is this. So what it is important that you consider is that there is also an order in the triggering that cannot be neglected. Moreover, another thing to pay attention to is that you have to avoid, as it was anyway with the impedances, you have to avoid to place a transverse SPD or a transverse impedance at the same end of a conductor where exists a longitudinal impedance or a longitudinal SPD. The second feature that we are going to see about the XGSLab 10.3 version is the on-tag parameter that is now available in the scheduler. So let's suppose we are in this very simple project with 4 different systems with a very simple tag A, B, C, and D, and we have also 4 reference points with the same name. We can now switch off all of them in this way and save. Now close, and let's go to the scheduler. We can import this already prepared table of parameters, and here we can also see what are the parameters that we set. In particular, let us concentrate on the on tag. The on tag, basically, it is the reverse of the off tag. So you say what the software has to switch on from the base project. That you state or is already containing switched on conductors, then those conductors will remain switched on. At the same time, everything that is not stated in this sequence of parameters remains as it is. So all the rest of the tags will remain switched on or switched off depending on their initial condition. Consider also very important that the on tag is in alternative to the off tag. So we cannot add an off tag parameter now. For example, if we do this, there is an error that forbids basically to add an off tag property because we already have a non tag. In case we wanted to add an off tag sequence of parameters, we need to delete the on tag parameter now. So we can keep this, we can confirm, and also we can launch. Okay, now the calculation is finished. We can see that we have many calculations that have been run. Some of them were not successful because we basically had the faulted electrode that was switched off, so the site to be energized was not found. But this was completely expected, let's say. What it is very interesting to do now is to close the scheduler and to go and see what has been yielded. So, for example, we can have a look at this first case. We can see that this calculation was successful because we have a result. And we can also see that we have A and B as switched on tags, and also are still present the tags that were present in the base project, but they are still switched off. The last feature that we want to show of this new 10.3 version of XGSLab is the possibility to plot directly the harmonic impedances in the TD module. So you can see here we have one of the examples that are available in the tutorial. We have the calculation that has already been run, and what we can find in the results, we can find also the harmonic impedance group box. Here we can choose the reference point for potential and also the reference point for current. As you can easily understand, the reference point for potential can be not only the injection point, but also some other reference point. Differently, for the reference point for current, you can have just the injection point. Now we can place modulus, and we can see the picture that is a picture like all the others, so you can paste, copy, store, and so on. For the modulus, real part and imaginary part of the harmonic impedance, and also you can plot the phase. Consider also that in case you are not satisfied in the width of the y-axis, you can set the smallest z to be represented. So in case you want the plot is stopped at 0.3, for example, you can set it at 0.3 ohms and regenerate the picture. So this is what you can get. Consider also you can also export the CSV file from here, so you can set it in this way, and as always, when you set the CSV file exportation, you have exactly what you have just plotted. So here it is really very effective in giving you all the values that you have on the plot in the software. This is all about the XGSLab 10.3 version. In case you have questions, we are here to answer to you. Thank you very much for your attention. Okay, so just a moment that we can share again our screen. Okay, so we hope that the presentations were useful to you. The new features have been presented, let's say, in their basic characteristics. So we have tried to be as clear as possible. I see that there is some raised hand. Just let me try to check. No, it has disappeared. Anyway, if you prefer to write down your questions in the chat, that would be, I suppose, the best way to handle this part of the question and answers, because in that way the question is clear 100% and there is no misunderstanding possible. So we are here to answer to you. Well, while we wait for questions, anyway, I remind you of the fact that we will publish the recording of this video. So don't be afraid of losing parts or having lost some parts of the presentations. Everything will be available for anyone who wants to watch again, and moreover, it will be published then, so you can run and run again in case you need. Okay, we see. Okay. Okay, Mauro, I ask you to.
Yes.
Okay.
I hope you can hear me. Yeah.
Yeah.
I was just waiting to see if there was someone else showing up. About the M-forces, the voltage can be chosen by the user. In the standard, if you want to compute the effects, it's not an input value required by the standard. And we have also performed some tests, and up to some megavolts, you don't see any influence of the voltage, or in other words, of the electric field in the total force. Of course, you can also try by yourself and see which might be the threshold that have an influence in the total force. If you consider the first slide of the presentation, you have the two components, the Coulomb force and the Laplace or magnetic force. The voltage will have a consequence on the Coulomb force, which is driven by the electric field, clearly. The numerical test and the simulations we have performed show that in a standard fault condition in which the current is truly high, you don't see any contribution of the electric field. But it might depend, or it might happen that in some other situation you can see something, and this is also why you have all the knobs and all the possibilities to tweak your simulation in this respect.
Okay, I thank you, Mauro, and also thank you, Alessandro, for the question. I hope that the answer was satisfying. I also read another question about the electrical and magnetic fields can be seen on enclosure of pipe and conductors along with the cores. Well, let's say that the magnetic and electric field can be seen there, The only thing that we cannot do is a specific calculation inside the enclosure. That is not our task, let's say, but the cores anyway, since they are conductors in the space, they are subject to the magnetic field. And also about the SPDs, basically the SPDs are impedances like all the other ones. And so in case of a transverse SPD, it works as if it works as a transverse impedance. And in XGSLab, the transverse impedances always connect the conductor they are connected to the potential zero. And by definition, in our software, the potential zero is at an infinite distance. So this is the connection that is applied. On the other side, the longitudinal impedances obviously connect, or better, they are added at the midpoint of an ending element of a conductor. So basically, you have an addition to an addition of impedance to an ending element of a conductor. That is the connection of the impedances, and so also for the SPDs that are basically impedances that can vary their values in case some conditions are satisfied. Okay, so let's start to, well, there is also an answer for Mr. Reddy in the chat that is about the fields on screen conductor. And there is also a question. Just a moment. And there is also, well, in the meantime, I answer to the final question, that is, can we define the impedance of SPD to Earth with which it is connected? Yes, we can. Let's say that when you set up an SPD, in case, in this specific case, let's say you have to use a transverse SPD, and you have the default value of the impedance, that is the high value of impedance, that is to say 10 millions of ohms. And in that case, that is the default value. You have to set the triggered value, that is the value of impedance in case of triggering of the SPD. Obviously, if you do not want to use a transverse impedance for that, because you do not want that it is connected to an infinite distance, that part of the conductor, you need to realize a real earthing system. So you have to set up a model for the earthing system, and you can use for the connection, let's suppose you want to earth a pipe somewhere. So you should model the earthing system, connect with a conductor, the pipeline, and the earthing system, and use a longitudinal SPD in that case for the connection conductor, and there you set the parameters of the SPD. So basically, you have two ways to handle the same problem. One, it is easier, let's say, the ZT, and the other is more realistic because it also allows you to consider the injected current there where it is, with so the consequent perturbation of the Earth potential. Okay, thank you to you, Mr. Reddy, for the question. There are other questions, please. Okay, if there is no other question, we can close this webinar. I take the chance with these final greetings to tell you that this is just the first of, let's say, a date that we would like to make something familiar with our audience, with our customers. We would like to establish this sort of rule that at each new version we make a short webinar in which we show the new features. So this is just the first time of something that will become usual for XGSLab community. I thank you for the attention and also for the high participation rate. We are very satisfied. And we also feel that this kind of way of communicating new features was, let's say, felt as necessary. So see you next time. And in case you have other questions, do not hesitate to write us some emails or comment the videos that we will publish in LinkedIn or in our YouTube channel. Bye bye. See you next time.